Good afternoon, everybody. It's my honor to be here, and I really did not expect this many people be in the room. So I'm really appreciative that you're interested in the topic. So, just to warm up, recently there was an avalanche of attacks on water utilities, done by Russians, hacktivists and so on. And I just picked two examples, and what has happened that in one case, for example, the attackers open valve to 100%, hoping to cause some impact, but unfortunately the system design was such that no matter what they've done, there was no any consequences. However, in another case, they kind of again done pretty much the same, open all the valves to 100%, and they basically overflow in the tower because there was no shut-off system which would shut off okay, I'm too full. And basically the nuisance, the effect was, basically loss of fresh water. But the point here is that it's not necessarily that if you successfully intrude into the system and execute an attack, that it will, in cyber-physical domain, that it will automatically translate in a physical effect or impact. No. Physics can play against, systems can play against you. So, and this is what this talk is about. So here, this is the video of what basically these attackers were doing. Basically, they got into the HMI screen, running around, looking, pressing buttons, changing numbers. Yep, basically. And it's not like they even understand what they do. They look at it, they try to understand. It's more or less like a guess. Yeah, here they change again numbers and so on. So yeah, it's basically, I have this video just to show you that this is the level of attacks which each of us is capable of. So that is not really threat actors we should be worried about. However, the news would tell us that this is basically the most horrific attacks possible on the planet. So many years ago, that's been already in 2012, I took a chemical plant as an object, and I thought well, if I would like to execute an attack on a chemical production process, what shall I do as an attacker? And there was absolutely no information whatsoever. I found one work in 2007 where there was mentioned 5 steps, if you want to hack SCADA, but there was no explanations, no additional information. But since there was nothing else, and it came from a person who works for the USA government, I saw that probably he knows what he's talking about. So I worked with it, and then I finally basically understood and described which all of the stages should be. They were correct because I went through all of them. And in 2015, I presented a work at Black Hat, and that was the very first work publicly presented when somebody really showed from the beginning till end what it takes to hack a production process. And it took me almost 1.5 years, and not because I am not intelligent enough or maybe I took breaks. No, I worked very hard, but it is a very laborious process, and we will understand why. So the entire purpose of this talk is to understand a little bit better what involves cyber-physical exploitation beyond that level of the cyber attackers getting into the HMI. And the current public presentation of about cyber-physical attack is more driven by overhype, FUD, just because they try to bring attention. Companies needs to get customers, get them scared and so on. But it's not really realistic a representation of what's happening. And for example, if you look all of this recent news Industria 2, Cosmic Energy, another attack, what has happened in Ukraine, in reality, this is the same piece of malware applied to the same type of infrastructure with the same type of control system, application. So it's not it's not an evolution, it's nothing new is happening, but it's always presented to us as if the attacker, strike again, But from the threat intelligence perspective, there is nothing else what I can learn from it. And since 2016 until 23, nothing else has happened. It is the same piece of malware, the same code. So let's take this influence approach, get rid of your limiting belief, and let's look at this like cyber-physical attack lifecycle, but we will start for the preliminaries. So cyber-physical systems, the term was started in 2016. Working on that domain in cyber-physical systems in 2010. There was absolutely zero information at that time. And I really like this phrase about Edward Lee, who says, like, it's a fundamental intellectual challenge because it is a close blend of engineering and cyber and physics, and we cannot really separate them from each other. And in like since then, like basically cyber-physical systems are everywhere. And cyber-physical attack, it's a digital malicious alternative of a cyber-physical systems to achieve an undesired physical effect. And so basically in the term we have these two components, cyber and physical. But when we even talking about the cyber, it's not simply about compromising or finding vulnerabilities, but it is like writing an exploit and with a purpose which will help you to achieve that physical impact. So that will not be something what you typically do in the enterprise infrastructure. It will be very difficult, different types of exploits. And what is missing in this term is actually because cyber-physical system has logically like 3 layers, and the most important layer is control system, the control layer. This is where the algorithm which defines everything what is going to happen with the cyber-physical systems. Typically, it's kind of not in the picture, and because like we still do not see really threat actors actively interacting exactly with the control logic, but that is the most crucial component of the system. And in order to understand better how we would be exploiting such type of systems, we need to understand that they work on the principle of control loops. It's a fundamental block of how any engineered system works. We have a physical process, we have sensors, which sends measure the state of the process, send it to the control system. There is a humongous amount of mathematics calculations and state checks happening inside, and then they decide what should be the control action. And during the attack, the attacker is interacting with control loops, even if the process is manipulated via the HMI. So yeah, the attacker has the opportunity to interact either with sensor signals or control system or actuators. So it really depends, like for example, since I've been working in this field for more than 15 years, I even have my own preferences. Like, for example, I don't like directly manipulating actuators. I like to spoof sensor signals and make control system to output command which I want based on the false measurements. So, because then system stays more stable. But again, there are so many nuances going on. And if you paid attention on the title slide, I put explicitly that I'm Doctor of Engineering. So yes, I'm an engineer, trust me. So yeah, just like an example. So we think that it is like you press a button like to start motor and it just starts, but not. Behind, the control system is checking millions of states in the control systems. And if the system is in a permissible state, it will only then start the motor. If not, it will not start the motor. So there is many more things going in behind the scenes than we see. So for example, I wanted to also bring you this example. So how does a physical vulnerability looks like? And so this is one of the chemical plants. And for example, like I want to burst the reactor. I want it just basically to explode. So for that, I need to basically rise pressure in the reactor. To rise the pressure, I need to rise the temperature because, and to rise it, to rise the pressure, yes, I need to rise the reaction in the reactor. But to rise the reactor rate, I need to rise the temperature. And because of how physical components, like basically entities, interact with each other. So it's a chemical reaction. The temperature is an exponent. So if I will rise the temperature just a little bit, the reaction rate will rise very, very quickly. So And then I can take a look that, for example, there is 3 inflows into the reactor. We can see that those inflows very large. The pressure in the reactor is controlled by the purge valve, which you see its size is very small. It's just 15 compared to the inflows. So as an attacker, so basically, if I will be able to rise the pressure very, very quickly, that purge valve will not be able to release the pressure fast enough. So I will achieve my goal. So that valve, that it is being so small, that is exactly the physical vulnerability. Now I found it. Now I need to start working backwards. How can I achieve increasing the temperature? I can manipulate with I'm losing the word, like with chemical components like of the reactants which go into the reactor. I can disable the cooling system. I can stop the mixture. And depending, like all of those components are basically controlled by certain assets. There will be cyber assets, and depending on where I can find the vulnerability, on which part of the network I am, I can go to that assets and I can start writing the exploit. But again, I still need to understand the control logic to modify it. So that is, so as you can see from this, so cyber physical exploitation really has very, very little to do with what we know about IT exploitation. And this is a little bit more even like, why is that vulnerability is happening? Because this is how the physics works, because of the time constants and so on. So all of this, again, this is all this knowledge so unusual, and it's all from the engineering domain. I have a lot of information on the slides, which absolutely not necessarily to understand right now. I put it there, so like if you are interested in the topic and want to understand it a little bit more, you can go back to the slides and check it on the slides. So there is like people sometimes saying like, oh, safety and security is just like the same, but just like 2 sides of the same coin. No, it is not. In reality, safety is like the whole even design of the plant, how it will be working, and even how the reactions in the reactor will be happening, like that is a process design. That is already part of the safety. Like defense, let's say, layers. And again, this is absolutely has nothing to do with security. So that is the relationship between them. So yes, the attacker need to get into the plant, and basically then security incident is happening. But then the whole game is beginning. The attacker will need to go through those layers of safety in order actually to be able to achieve the physical impact he wants. But again, so ability to compromise software or finding vulnerability in the protocol really does not immediately translate, not even fastly translate into the physical impact. So, but in reality, control loops, like we have many different control loops. So it's not only the controller who is controlling the process, but also the human. There is many different applications there which analyze the data and do optimization, adjustment to the process. There is support applications. So there are many opportunities where the attacker can interact with the process and have it cause an impact. But depending with what type of those, like where in this control loop the attacker will be launching the attack, their ability to achieve certain impacts will vary. And like really a prolonged, like basically physical, like for example, breakage effect is only possible if the attacker will be working at this, like at the level of the control system. This is where mostly I am working. I'm working like on really hard stuff. But in reality, what has happened in the past, like even like 5-7 years, like the advancements happening so quickly. So now a lot of applications are moving to the cloud. So getting access and like if you get into the cloud of these applications, there is literally almost like direct links to the assets which are very close to the physical process. So it's really like if in the past you would really need to get into the plant, like move laterally to reach the assets. Right now things has becoming a little bit much better. However, again, it will be difficult to execute a very granular, a very damaging attack from those applications. Nevertheless, you can really still do a lot of like unpleasant things. And if you look at the ultra brief history of targeted operational technology, industrial attacks in the recent years, which I'm talking exactly targeted attack when the attacker had something specific in mind. Oh, something is okay. Basically, there should be a square. It disappeared somehow. It's interestingly enough, it just happened that those were all Russian operations. But interestingly enough, since Triton in 2017, we have not seen any improvement in complexity of executed cyber-physical attacks. And there is a good reason for that, because Russia has done a lot of testing in the live environments, for example, especially in Ukraine. Triton was in the Middle East. And they've realized that, it's hard, it's complex. And basically what we see right now, it's more or less all state-sponsored threat actors took a step back just to say okay, let's reconsider what is possible, what is not possible. So we kind of have this a little bit like a tiny break. But in reality, again, we have not seen, even though in the news you would see oh my gosh, there is more threats to critical infrastructures, potentially yes, but not in terms of those fatal or dramatic effects, how that's described in the newspapers. However, what was also happening in the last years, and 2 years ago, I gave a talk here also at SecTor about that. So, for example, there was a Vulkan files leak, which presented basically that was basically very top secret information about Russian cyber operations, and I had an opportunity to analyze that information, all of that leak. So I presented it here, and actually, it's very clearly shows how all the cyber operations is now being moved under military command, and this is where the game is changing entirely. And actually, Russia has started doing that, basically moving those operations since 2014, and that is what we have seen in Ukraine, this massive testing of capabilities, because that is this is really military tactics. However, Russia got a lot into the news, and China suddenly also became interested in cyber-physical exploitation. Well, why not us? So in the last 3-4 years, approximately 3 years, China started getting into the news that they massively intrude into the critical infrastructure. And if you look at how the cyber operations structured in China, there is a fantastic talk was at Black Hat Asia. It's all already also militarized. And for example, operations in USA, Israel, Iran, and North Korea, they are also in the military of command. So a lot of these operations, basically all strategic and tactical operations are moved under military command. What is unfortunate is that the defense stays civilian. We are not really playing the equal game. So this is for example, so I said that the complexity of cyber-physical attacks has not changed since a long time. But what has really changed is intention. We do see the intention that all state-sponsored attacks, at least in the future, they want to have these capabilities. And that is why we need to worry about. But we still don't know how complex it will be. But by the end, we will see that what kind of attacks we should expect. This was just an example how, for example, Russia manages their cyber operations. You have physical objects, and then you do recon, assign tasks, and so on. And it's data goes into the GRU and so on. So just we looking again in this timeline between of how what the attacker needs to do in the target environment, and somehow he needs to do something to get that trophy. But what that something is? So complex attacks typically described in terms of life cycles or kill chains, and we have a lot of them. I'm sure you've seen all of them. However, none of them is really describing or helpful for the cyber to understand what cyber physical attacks. So typically in the IT oriented life cycles, you will see this complete mission or action on objectives, but what exactly should they be doing? There is this SANS ICS framework, but this cyber physical development of attack is just one stage, develop. How? So, and even like MITRE is the most like kind of tailored to cyber physical attacks, but it is helpful only when the attack is already designed and executed. Then you can break it down into certain like basically technique and tactics. But it's not like you take techniques and tactics, put them together, and you are able to basically have an attack scenario. So we don't have really alternatives. And embedded, I have it here because it's very useful for cyber physical, but for writing exploits. So basically, like after I presented the cyber physical attack lifecycle in the USA, I applied it to many different types of systems. I understood that I really need to add 2 more stages, prevent, response, and feedback, because that is kind of like, that actually reflects this feedback loop, which we see previously. So, and, you know, I've gave a lot of briefings to this national security agencies. I've trained military and so on. So I know I see threat actors reading my materials, and which is, well, yeah, probably like interesting to observe and so on. But like I have not observed really that civilian is kind of using this attack life cycle. So now I'm kind of I'm developing a set of trainings to talk more about this cyber physical attack life cycle, to kind of bring more a little bit awareness how these attacks are happening. So, but of course, you know, like the most important, like, of course, none of the attack life cycle, like attack is happening like in these logical steps. So it's basically the attacker will always need to go back and forwards to different steps, skip certain stage and so on. So like not even all attacks will have all of those stages, and not necessarily, sometimes they are not necessarily, but sometimes not able to achieve what he needs in certain stages. So he will need to skip it and work without it, which always complicates the attack. I have here a vocabulary because I will be using those words. So attack scenario is something that complete. What do you want to achieve in your target environment or system? Attack stage, basically, yes, it's a set of activities within this attack phase, logical attack phase, and attack instance. So within any of those stages, you will have attack instances. You will need to design exploits and basically think of them logically design and then implementing the exploits to actually achieve what you need to achieve at each stage. I will not be able, because time is very short, this is such a complex topic, and I will not be able to go into the details of all of this, but I will just want to give you a feeling of how, like, what do you do at each stage. So, and again, access, it's not really access stage. It's not really about like, hey, how do I bridge the perimeter? Like, do I go via phishing and so on? That's not what we think here. Here we think about like, what are the typical entry points into the industrial environment? Where I can find necessarily information, because information is everything to design an attack. And this is where the supply chain and espionage is playing a great role and so on. So large ecosystem, because like vendors and certain like download, like we've seen the attacker also using large ecosystems, like kind of to introduce malware to the industrial environment. And for example, so like once you get the like kind of, it's always easy to find the documentation even in the enterprise domain. And when you look at the documentation, you want to find like all of those access points, because it's very easier to get closer to the assets which you need than moving laterally from the, for example, enterprise domain. And one of these like pictures on the like higher than there is like GPRS modem, which is now became very popular. One attacker, they really like this GPS and satellite models, and then they get exactly closer to the attack needed assets. And this is basically the stage where happening a lot. So every state-sponsored threat actor, so basically every country is now massively intruding into the industrial environments to establish persistent foothold. And there's so very little analysis, like what is really, how to explain that, what really the industry, like basically asset owners or operators of the industrial infrastructure should be protecting. For example, all of these like VPN routers, like very popular in Europe, it's almost everywhere in every control cabinet. It has SIM card. Russia is absolutely great in getting remote code execution of these devices by simply sending an SMS message packet to these devices, and they are already on it. And when I try to talk about like with the operators, like, hey, I mean, like you need to disable GSM, like you need to like maybe get another model, like, well, whatever, I don't know, maybe it is. So yeah, it's like a lot of actually governments are now also analyzing larger like systems like Crane or like solar system and so on, because they start finding like very subtle backdoors in all of this environment which grant access to this system. So this is where happening a lot. And then, of course, you know, like attackers are massively going after the supply chain for the information, again, to find like many vendors, integrators, like have remote access to this environment. It's easy to compromise them and move laterally. So there is massive amount of attacks going against the supply chain. So this is where we really see a lot of things happening. And then once the attacker is already in this environment, he needs to understand it. And this understanding of the environment in the industrial domain consists of two parts. It's like reconnaissance of the infrastructure and then process comprehension. So what is the environment is doing? But also, like, so basically this is how it would look like. But when we look at even at the network infrastructure, that will not, reconnaissance, that will not again be your typical recon which you do in IT or enterprise, because like scanners like Nmap are not really very useful to you. So this is like an output how an Nmap would scan the HMI panel. But the amount of information which it will provide is just like not really very helpful. And for us, in order actually to exploit embedded systems, we need to know a lot of very specific information about it. Otherwise, we will not be able to really write an exploit for it. So we always need a very specialized scanners. And like a lot of researchers now start writing such scanners, and they are like often specific to specific models and so on. So there are some tools at the moment, but again, so the diversity of the devices in this environment is so large that almost always attackers will be missing the scanners. And we have seen, I've been on several incident responses for such large attacks, and we can see that the attacker often bring the scanner with themselves. So in the reconnaissance stage, just try to understand assets available, interdependencies, use protocols, and so on. You try to get actually general understanding about systems. So this is one of the environments, like it's realistic diagrams. And for example, I'm immediately drawn here to the solar system, because like there've been a lot of research on this system and I'm interested in it and I understand how the physics and the electronics works there. So then I will start, of course, researching like, okay, they have this model of solar system and what is available, like vulnerabilities, information, diagrams, and so on. And then, like, this is basically how we understand the environment. And then we actually, to understand process comprehension, what exactly this environment is doing, like what it is producing, how it is controlled, how it is built environment, because many environments, again, depending, like cyber-physical systems, there is such a huge variety, you know, like it's a ship, it's unmanned vehicles and so on. But for example, if you talk about plants or ships, you know, like they're so large, you need a bicycle to move from one place to another. And of course, then also operating conditions. So this is basically the type of documentation you will need to work with. And it's very, like you need a subject matter expert to really understand it. And even me, like, I mean, I am an engineer, but whenever I take a new environment, I need to start from scratch. Yeah, like basically this is more examples of what information you need to collect. And what is another really big misconception is that if the attacker is able to intercept the traffic, he won. Nope. Most traffics, once you look into the packet, they tell you nothing. It's a register. What is behind that register? What are those values? You have no idea. So in most cases, looking just in the traffic is absolutely not helpful. So the attacker would need to actually find a lot of documentation to able to correlate it to actually, for example, starting from pumping the diagram, looking into the traffic, and then actually so that finding that specific pump and basically be able to send commands to a specific pump, it's a huge process, which follows, like, I'm not going here in the details, but it's more, that process is about correlating tags. So because what you will see mostly in the traffic is tags, and the tags are different between different systems. You need to find files which map them and so on. So whenever you see presentation of cyber-physical attacks, maybe like in an expo hall and so on, and say, oh, that was so easy, I've done it, just because they know the system, they know where to send what. The attacker, when they are in the new environment, they have no idea. And that is actually, that part, one of the most disgusting and difficult and takes time. The control, and this is where we kind of finish in the static understanding of the system and we move into the control stage. Now we need to understand how dynamic, what is the dynamic behavior of the system. Whenever, because we are talking about physical domain, whenever we change something, something else is changing as well. So we need to understand like how much I can change the process. Like, can I be, is the system staying stable? In most cases, you will try to move the system in some weird places and the system become unstable. So that is an understanding this dynamic behavior of the process, and there is absolutely no tools or guidance how to do this. I went through this process many times. I've tried to apply standard tools. I've developed my own algorithms. It's very, very, there is no really structured way. It's more like, it's like feeling. And one of the most difficult things that I always encounter is that, like, control loops, whenever you try to like move the process in not unhealthy state, you will have the control loops will be misbehaving and you basically cannot properly control the process or fail entirely. So all of those are very difficult process, like things to achieve, but you need to do them. And in this case, and this is why, like, for example, like discrete processes are so much more easier to exploit than the continuous processes. And this is me trying to create a mental map of one of the plants or chemical plants are doing. So that's a lot to do. Yeah, and basically in that stage, you also enumerate controls which are available to you and so on. So then after we go, like, because the control stage will tell us what are our opportunity. And only then you know, like, okay, now I know what is system is capable of doing, or I can do without, like, system stable. Then you can start designing a very detailed damage scenario, very, very concrete. And this is where, like, this is just an illustration that we have these three phases, damage, prevent, response, and feedback. We will look at them. And actually, like, you want to understand, like, what can be done to the process. So, like, for example, this is my personal classification, and I can tell you that equipment damage is very hard to achieve. Service uptime was very easy to achieve. Production damage is medium, can be easy, can be not. And compliance violation can be also quite different. But again, depending on the attacker goal, they can use any of those objectives. And then this is, for example, a taxonomy of the physical breakage. Again, you need to start thinking as an engineer how the system is breaking. And the easiest part, like the easiest way actually to do so is go into the accidents database and look how the systems failed previously, or actually go to the library and find a book which tells, like, how to optimize piping infrastructure, because they will tell you how to optimize it, then just do the opposite, and you basically have your damage scenario. This is one of the examples how I was killing a catalyst, and interestingly enough, like, even because I designed a fantastic damage scenario, but I skipped the control stage, and once I moved to the damage stage, I realized that I cannot actually execute what I planned because the system was not playing along. And this is another example where I, as an attacker, did not win because I was trying to kill a filter in the water utility, and the membranes and the filters are basically failing at the toolbars. But it was a complex attack, design and execution and so on, but the maximum pressure which I was able to achieve was 1 bar. Not enough for a damage. Like, well, successful design, very good design, successful execution, physics does not play alone. So the attacker is not almighty. And again, like here I did not really work on the control stage, but that is something where I would be able to figure out in the control stage. And for example, control stage would be very important for like the state sponsors attacks, because like you want to have a full understanding of the system and potential to create damage. And then you create the damage at the opportune time. So if you skip the control stage and just go with the discovery and then try to move immediately to a damage stage, you might have this effect that like, I thought it is possible, but it is not. So you will not have your attack at a strategic time. And what is going to happen? I actually realized that I will not going to go through all my slides at all. I'm just in the at the half. I was very super optimistic. I apologize for that. But if we will finish the attack life cycle, then you will see how, like for example, like how it can be applied to a physical system like real-time locating systems. And the point was there that the vendors are not properly testing, like basically they are not using like cyber-physical risk assessment to understand how to protect their system. And they're missing even the components where which like basically part of the system which they need to protect, and this is where it gives the openings for the attackers. But yeah, so what we are going definitely to expect in the future is this easy buttons attack, something which is very reliable, very simple to execute and does not need really a lot of discovery, comprehension, and so on. So for example, like placing a rotating equipment to rotate at his natural resonance frequency, it will make it break. Or for example, opening the breakers in the energy substation. So that is definitely something what we are going to see. Yeah, so when you're executing an attack, the whole control system, the safety system, the operators will be basically fighting against you, because you're trying to bring this process from the equilibrium, from the and it will, so all of those systems will be working against you. So the attacker need to make sure that those systems will not fight back. And there is a lot of approaches here, and depending what you need to achieve, like for example, like one of the things which you almost always needs to do is just like hide the alarms, and you can suppress them. You can basically easy patch the whole instruction in the control logic. I like to work with sensor signals. I hide, for example, those high frequencies by filtering them out and so on. So there is a lot of approaches what can be done. So this is another work of mine. I designed a very powerful algorithm which allows me to accurately spoof sensor signals. And actually I was approached by one of the government who told me that they've tested it and it's really very good, and asked me, how do we, tell us the secret, how can we detect it? And you can detect it. I told them what they should be looking for. Yeah, and then it's very, very important to know what are the unwanted states, because that is like the system will be, you will not be, so if certain states are unwanted, but those are actually which lead to the damage or degradation, the system will be basically making compensative actions. And by knowing them, the attacker can actually prevent those systems from executing. And there are, again, tons of approaches for that. Yeah, so and very, for example, yes, so this is an interesting example here. So the interlock conditions, when we were working with this water filter, it turned out that the condition which would allow us two exclusive water flows flow together was a completely different PLC, and it was just a flag. So this is kind of a type of examples or surprises which you can discover. So the attacker would need to go into completely different network segment, exploit completely different PLC just because he need to override that flag. Yeah, so and when you like what we've discussed, like in the attack effect will propagate like in certain directions, and the attacker need to know how far, because then he will need to prevent this response in multiple parts of the system. And obtain feedback is about like monitoring the progress and registering success, because in most cases the attack is not instantaneous unless it is like open breaker. The attack will take time. The attacker need to monitor, am I doing right? Because the attacker is sitting somewhere remotely. And in most cases, because the attacker is again putting the system in some abnormal state, there is no pipe roundness sensor. This is my attack of the cavitation bubbles. I was killing the pump. Like there is no sensor which will detect bubbles. So there could be, for example, like I needed to measure the concentration of chemical in certain part of the process, but there was no analyzer. So you will need to find a lot of like kind of compensatory like ways to measure the process in like through the proxy management, through some calculation, going into the control logic and maybe finding some values of variables which can be helpful and so on. So it's a lot of like kind of creative approaches, and like in the real attacks we saw that, for example, attacker likes to basically catalog and like progress of the attack and like sort of command line, like, and they write into themselves script success, run success, like, well, we're all humans. Yeah, and this observation, like obtain feedback, is also very important, for example, to coordinate the exploits, different parts of exploits. So it's very difficult. So you typically would need multiple exploits, and it's very difficult to make them communicate via the electronic, like over the wire, because I mean, it's also not stealth. But the most easiest part is actually to make the exploits detect certain states in the physical process and then like kicking in at a certain time. So that is much more easier to implement, and that will be then the control loop for these implants. So yeah, there is a lot of, and then like, because like you typically will be working with a control, like with embedded systems which don't have memory or CPU, you need to write very lightweight approaches. So as you can see, it's a lot of consideration, non-trivial consideration. And the deeper we go, the more you see like, well, who would be doing that? But it's all doable. And then cleanup, it's actually a military term, so you conducted an operation. And cyber-physical attacks will have an impact in the physical world. And you can't erase the logs and just like, oh, nothing happened. So it will be there. So what you want to do is basically, first, during that your attack, you want to kind of prevent that the operators of the process will successfully identify what is happening with the process and what is causing it. Like after the attack, you also want to confuse the forensic investigations, because like unless you want to like be discovered and known for what you have done, you actually basically want to create a forensic footprint which will suggest something else has happened. And it is very, very creative process. Like I listed some couple of examples, like, and again, one of my examples, I also changed, like I can, because I'm a telecommunication engineer, I'm very comfortable to work with sensor signals because it's just a signal. I I can work with signal processing to actually make it as if it is the signals are delaying against each other. And then if you start conducting forensic investigation, you can see that this event started before that event, but it's actually false. And that is actually confuses the forensic. So there are a lot of different creative approaches. But again, depending, like you might want to have a cleanup or may not. Yeah, so this is just basically a summary of all of the stages. And I am really apologize that I just reached basically this part. Yeah, in the conclusion, so like after this, I had like one section on what we are going to see in the future, and the exploitation of these processes, like of the cyber physical attacks, will mature and they will be happening. And especially because like a lot of things has changed in the last 3 years, like especially, so first of all, like a lot of public research was published. I'm in the Black Hat Review Board. We see this enormous amount of very advanced research for the cyber physical systems, like applications. So that is already like blueprints which you can take. You are not starting from the beginning. There is a lot of tools and scanners developed. So the attackers already right now, like compared even like to 7 years ago, they're starting with such a huge baggage already, like positive knowledge base. And the most important is that the like majority of the tasks which like stages of tasks, which each stage they're very laborious and require subject matter expert. With the involvement of AI, things will expedite dramatically. You can analyze like in automated way literature, catalog knowledge, and so on. You can analyze process data, finding a lot of interesting, like vulnerable states and so on. So definitely with this involvement, and especially AI, because a lot of these stages will be shortened dramatically, they will be assisted. Plus, they can, like AI can really, to a certain extent, replace the subject matter knowledge. So yeah, we are going to see a little bit more, but we're definitely going to see like the attacks will doing all of these complex attacks is a little bit laborious, and you will only do it for very strategic targets. Why still we need to learn about them is just to understand what is a realistic threat, what is not realistic, how to conduct risk assessment and correctly make correct estimations. Thank you very much for your attention. I really apologize that I didn't go through all my slides.